Hey, it's Tony from Adafruit, and in this video it's going to be part one of a project to make what I call the circuit walker sneakers. So these are shoes that can detect movement using Circuit Playground. And this is actually kind of a cool pair of sneakers that I have right here. These are some Converse Chuck Taylors that have this cool circuit board pattern. But this is a Circuit Playground board that's just attached, zip tied to it. And if I kind of kick the shoe as if, as if I was taking a step and just, giving that kind of kick movement, you can see the lights on it kind of flash red for a moment. And that's because the board is actually detecting the step that I'm taking. Now I'm holding the shoe like this, with my hand, but when I actually put it down on the ground and try it out, it actually works surprisingly well. So this is a version of the Firewalker sneakers, which I'll show a picture of and I'll link to a guide, which is something that I consider maybe a classic Adafruit project. If I think of the iconic projects that Adafruit has created, like the Pi TFT, the Firewalker sneakers are definitely right up there. And it's basically a pair of sneakers that light up when it detects you take a step on the ground. And you can animate neopixels and do all kinds of fun stuff. So I thought it would be fun to make a version of those shoes, of the Firewalker sneakers, that use Circuit Playground, so that just use this tiny board that maybe you can see a little more easily like this. This is Circuit Playground Classic. There's also a version of this called Circuit Playground Express that has a little bit fancier microprocessor. And this project will work with both versions, either the Classic or the Express version of this board. But basically, I wanted to make something where, with Circuit Playground, it's our all-in-one electronics learning board. It has these 10 neopixels around the outside edge of the board. And it has an accelerometer in the middle of the board so that it can detect things like movement, motion, gravity, orientation, things like that. So with those two devices, the accelerometer and the neopixels, I can pretty much approximate the Firewalker sneakers project. So I can use the accelerometer to detect when you take a step, and then light up the neopixels, like animate them in fun ways when it detects that you take that step, so that it can make a really fun project. And the great thing is this is much easier to build than the original Firewalker sneaker project. It's maybe not as impressive. I wish I had a pair of them, but it is actually a bit of a challenging build, the Firewalker sneakers, because you need to glue a strip of neopixels to the sole of your shoes. And then you also want to make it a little bit flexible in some parts to it. We've actually done two versions of them. And the way the Firewalker sneakers originally worked is you put a piece of conductive paper. I forget exactly what it was. I think it was like we'll look at the guide and we'll see. But you put something in there that is basically like a force-sensitive resistor, so that when you take a step down, you really push down hard against the material that's lining the bottom of the shoe. It can detect that as a step that you're taking. And then it'll light up the shoes, but there's a lot of tweaking you would have to do with the original project. So not an easy build, very impressive build. This will be a little bit simpler. You basically just take a Circuit Playground, put it on your shoe, and then it should hopefully be good enough to detect, when you take a step. And right now this is just flashing red, but we'll see in a future version of this video, we're gonna add some animations and go crazy. So in this first video, I wanted to just look at a step detection algorithm using the accelerometer on Circuit Playground, and we'll look at how to maybe take this algorithm, run it on Circuit Playground, kind of investigate what it's doing. It's doing some somewhat advanced signal processing, so you have to do some low-pass filtering. And if you're really curious, I guess I'll cut to the chase. And in this video, we're going to implement a Butterworth low-pass filter, an IIR filter at 3.667 hertz cutoff frequency in Arduino. So if you're curious about that, that's what we're going to do. If that makes no sense to you, which it almost made no sense to me as of a few days ago, but hey, I've boned up or brushed up a little bit on signal processing theory, so hopefully I can explain some of this in a little bit of detail, but I'm not a signal processing expert. But that's the core of this project. Basically, we're getting a signal from the accelerometer, and if we apply some processing to it, like some filtering, then we can do things like realize that, okay, the shoes may be moving around like this, maybe you're just slowly moving your foot around, but when you kick it up like that, you have a sharp impulse, a sharp little jerk of movement, then it detects that, and it can do something like light up the neopixels on the board. So let's get started. Like I said, this will be part one. I'm going to do multiple videos. This is going to be done using Arduino to start with, and then in a future video I'm going to look and see if I can do a version of this using CircuitPython. So in a lot of my projects I've done recently, I've started with an Arduino version and then done a CircuitPython version, just to kind of show that you can do most things with both systems. This one could be challenging though, so we'll look at the Arduino version and we'll see kind of what it has to do, and then eventually we'll look at in a future video maybe a CircuitPython version of this that may or may not be able to use the exact same algorithm for this, because again, there's a big performance difference for this. And eventually I'm figuring this will probably be maybe 3 videos. In this video we're going to look at the step detection algorithm. I think in the next video we'll probably look at some fun animations and actually make this a complete project. And then in probably the 3rd video we'll look at a CircuitPython version of this. So let's just kind of dive in. We'll jump into the main shot right here. And I'll start with, like I said, a quick mention of the original Firewalker sneaker project. So I'll put a link in the description below when this goes up on YouTube so you can go to all of the web pages I mentioned here. This is the original project for the Firewalker sneakers. Like I said, this is an iconic thing. If you've ever followed Adafruit, you've probably seen this project in the past. It's really cool. And it's basically just a strip of neopixels that you put around your shoes, and then it detects when you take a step. It can detect that and then animate them in fun ways. And you can see from the tools here what you need to use. So it's called Velostat. That's this pressure-sensitive, conductive kind of sheet. It's, basically when you press it, it changes the resistance. And so what you do is you put that Velostat, you cut out like a foot shape and you put it inside of your sneakers, and you put some neopixels around the outside of your sneakers, and you have a little board that listens to the resistance, that reads the resistance from that Velostat. And then you have to kind of tune it a little bit, and it goes through in the guide. You kind of take some practice steps and see what the resistance value looks like when you take a step, and then you set that value there. So it's a little bit fiddly, but it's, again, a really impressive, cool project. But you can see, like, it requires a little bit of work. I mean, you're going to be doing some gluing and assembling a bunch of things. So again, the Circuit Walker version, I figure, it's not going to be as impressive. You're not going to have the whole shoe lighting up, but it'll still be kind of cool that you'll put this little thing on your shoes and be able to see a change. And in the upper right-hand corner, you can actually see I have 2 shoes right here. So both of these are running this. And so you kick them up and they light up in different ways like this. So that's the first version of the Firewalker sneakers. There was actually a follow-up version that simplified it a little bit. So this switched, instead of using the Velostat, which changes its resistance based on the pressure of you stepping, this used a little vibration sensor, which is the really neat little mechanical sensor in the shop, where basically there's just a spring and a ball inside of it, and when you vibrate it enough that it overcomes the force that the spring in there has, then it'll make a connection and basically turn into a switch. So it's like an on or off, like vibrate, not vibrate kind of signal that you get from it. So if you put that on a shoe, that gives you a simpler, when you take a step and you hit the ground, if you use the right sensitivity of the vibration sensor, then it'll give you a pretty good detection or a good idea that, hey, you've hit the ground, that the force is kind of causing it to vibrate, and it can send off, a neopixel animation and things like that. So this one's a little bit simpler. You don't have to do the Velostat and all this tuning of it. It's more of a digital output, a digital signal from that. But let's look at, okay, how can I do this with Circuit Playground, our all-in-one electronics learning board? So we've got the accelerometer on there, like I mentioned. Unfortunately, there's no there's no vibration sensor necessarily built into this. There's no Velostat thing, although it does have an analog input, so you could hook it up to a resistive sensor like a piece of Velostat. You could build the original Firewalker sneakers with this, and even the follow-up ones, you could still use the vibration sensor. But can we use stuff built into Circuit Playground? And it turns out, yes, we can. So in Circuit Playground, there's a little accelerometer built into each of the boards, and it's in the very middle of it. It's this tiny little square chip. And that is basically a device that can measure a force, like the force of gravity applied to it. So when the board is kind of sitting here, gravity is pushing down, and this chip can actually detect that. And if I move the board around, it can actually detect in 3 different axes of motion what the orientation is, or which way gravity is coming from. So that's one thing it can measure. So, or one useful thing that you can use accelerometers for is figuring out, is this flat on the table, or is this held up at an angle potentially? How is it oriented relative to gravity? But it can also just detect force. So like me waving this board around is applying a force to it. And so that's a value that the accelerometer is able to detect in 3 different axes of motion. So like forward, backward, up, down, and then left, right also. So you have all 3 of those axes. And it's the same technology that's in your smartphone. So when you look at your smartphone and you turn it from portrait to landscape, there's an accelerometer in there. And that's just figuring out, okay, how is this board positioned relative to gravity? And then it knows to change the display based on that. And the cool thing is, since every smartphone pretty much has an accelerometer these days, these devices are super cheap. I mean, they used to be probably 20 years ago, 30, maybe 20, 30 years ago, these were like high, expensive, military grade pieces of hardware that now everyone has in their pocket these days. So that's the fun stuff you get with technology. So the question then is, can you use an accelerometer to detect steps, like the movement of, if you had an accelerometer on your shoe, can you detect that movement, that kind of regular motion of your foot coming off the ground and then going back on the ground? So it's kind of this cycle, this oscillation. And it turns out, yeah, you can. There are a lot of different ways to do it. And if you search around, there's actually a lot of really good papers that cover this topic of step detection using accelerometers. And it's actually really popular because everything like these little fitness gadgets. Oh, I don't have mine on right now, actually. So I have this little band that I wear on my wrist that, monitors heart rate and all that stuff, but it's got an accelerometer in there also. And it's measuring things like forces, and it can tell you how many steps did you take during the day. So did you take like 10,000 steps if you're trying to hit some goal? And that's using an accelerometer and applying some logic to it to figure out, just based on the forces and the movement I saw, like maybe my arm swinging, if it's a wrist-mounted accelerometer, can I figure out the number of steps there? And I found a really good paper here. I don't know if it was ever published, but it's some research that I think some students did that I found on GitHub here. And it's a really good walkthrough of how they built a step detection algorithm. In their case, they were using an Android phone and the accelerometer built into the phone. And then they were able to figure out, is a user walking and how many steps did they take? But the great thing is, in this paper, they walk through their whole thought process of, they started with a basic idea and then they just refined it in a few different ways. And they eventually came up with this adaptive jerk pace algorithm, which, we'll look at, I'll talk a little bit about. But I looked at this paper and it was kind of interesting that, just looking at the basics of what they're doing, I don't have to go all the way and implement the entire algorithm that they have. I actually just implemented about half of the algorithm. But even with that, it's good enough to do this kind of jerk detection so that when the shoe moves forward or moves up, it can detect that as a jerk and then consider that a step that's being taken. So this paper is really good. I'll put a link to it again in the description below. Take a look through it, skim it. You don't have to understand all of the math and kind of what's going on. I'll walk through it in this video. But this is a really, really good resource to look at how this works. And at a super high level, basically in this paper, they started with an idea of, well, let's just look at the raw accelerometer values. And again, the accelerometer has three axes. There's an X, Y, Z axis. They're all perpendicular to each other. So with those three axes, you can figure out 3 dimensions. And so the first step is kind of like, well, which axis do you look at? If the board is held on a shoe like this, then maybe the up-down axis is like the Z-axis, for example. So I want to detect, moving up and down on the Z-axis. But what if the board was held like at an angle like this, potentially? So now the up-down axis is like the Y-axis. And does it still detect steps and jerks? And actually it does in this algorithm. Oops, I hold it a little closer. Can you make your algorithm resilient to the orientation? Can it figure out which axis do I need to look at? And it turns out, yeah, there's an easy way to do that. So you can figure out the magnitude of the acceleration vector, because basically that accelerometer gives you an XYZ acceleration value. And if you take all 3 of those values, that's a vector, or basically like a direction in space, in 3-dimensional space. A vector could be pointing straight up, might be pointing this way, might be pointing that way, or whatever. But it's a direction. It's saying, hey, there was a bit of acceleration in this direction. When the shoe moves up like this, the acceleration goes up like that. But if I move the shoe left and right like this, then the acceleration kind of points in that direction or points in this direction, the opposite way. So you can figure out the magnitude of that acceleration vector, which gives you a value that doesn't depend on exactly which axis. Like the magnitude is just telling you what was the strength of that acceleration. I don't care what the direction was, whether it was up, down, left, right, in a circle, whatever. I just care how strong was it. Was it a very quick, high jerk up, or was it a very slow, smooth movement? Was it not very strong? What is the magnitude of that value? So if you take the magnitude of the accelerometer value, and that gets you a little bit closer. Now you don't have to figure out, okay, do I look at the Z-axis or the X-axis or the Y-axis, and how is this thing oriented? Forget all that. Just compute the magnitude and look at the magnitude of that value. And then what they do is they apply, so they looked at that value and they saw that there's a lot of noise to it. You know, you get what's known as high frequency and low frequency noise. So high frequency in the sense of, you know, as I'm holding this, maybe my hand's shaking a little bit, you know, or maybe even just the forces of you know, the object itself sometimes. I mean, just the forces in the room, it might be causing some noise to be seen, some very, very small, fast changes. But then there's also this low frequency component, so a much slower change. You know, imagine like me taking slow steps or something like that. So this thing is moving really slowly, and the signal you get from the accelerometer is composed of both that low and high frequency noise. You just get everything together there. So what you can do is you can apply some filtering to remove some of the frequencies you don't care about. So I don't care about all these little high frequency shakes and jitters and things that I might be getting in random noise. I just care about this slower movement of, you know, the shoe kind of going up and down and being jerked up and down quickly, but not too quickly, so to reduce some of that noise. So they apply this low pass filter, which basically says, ignore the high frequency components, cut all those out, and just take some low frequency components. So get rid of the high frequency stuff, take the low frequency stuff, and then let's do some computations based on that. And we'll look at some examples here in a moment. We'll apply a low pass filter to the accelerometer and see kind of how it changes and what the data looks like. But then their first kind of stab at this algorithm was to say, okay, we'll filter the accelerometer magnitude, and then we'll just set a threshold value where if we see a jerk from that filtered value, from that filtered data, if we see it jerk above some threshold, like let's set a value of you know, 1.2 gravities. So if your step kind of causes a force of acceleration that's a little bit higher than gravity, then it can detect that and say, okay, that's our threshold value. And they actually saw that, you know, this works with a little bit of tuning. If you go through this paper, it explains a little bit. This was kind of their first stab at it. And they can make it work with like one user who maybe has like a really aggressive stepping style, you know, boom, he's like really moving his foot fast. But it might not work well with someone who has a softer step, you know, someone who's, you know, very, very quietly kind of just, you know, barely moving their shoes in that case. So that's one kind of issue with this first attempt at it, is they set a fixed threshold, but then they realized that's not going to work for every user. Now, in my case, since I'm doing some setup ahead of time, and since I'm kind of building this sketch, and, you know, this is not like a finished product that I'm going to put in a shop that someone can buy and that I expect to work with everyone, I can live with some tuning. So, you know, I figured for my first attempt at porting this algorithm over, let's just start with this simple threshold approach, where I just set a static threshold, and when the filtered force exceeds that threshold, then I'll consider that a step. And we'll go through and we'll see examples of this. We'll dig into the data and see how this works. Now the paper goes on and it actually figures out how to overcome even that problem of how do you deal with someone who has a light step versus a harsh step. And it eventually builds this adaptive algorithm where it will compute this average jerk, which is kind of the average difference in the high and low values in these oscillations, and it will actually update that average over time so that it kind of starts out with a fixed value, and then as you take steps, the algorithm kind of tunes itself so that it will figure out what is this average jerk step they call, and then it will set a threshold based on that average jerk step value, which makes sense. It's kind of nice in that, you know, with their algorithm, presumably anyone, whether you take a soft step or a heavy step, would be able to put these shoes on and it would eventually figure out and start detecting their steps. But like I said, we'll keep it simple. And with this video, we're just going to do this filtering and simple threshold approach for this. So in the paper here, like I mentioned, they start with taking the magnitude of the accelerometer, because the accelerometer they're using is the one that's built into a smartphone. It's just like the accelerometer on Circuit Playground, so it has these three axes, the XYZ axis. And so this is the equation to calculate the magnitude of an accelerometer vector. You know, given an XYZ vector or direction, this calculates what is the magnitude, or, you know, think of how strong is this. Like a very strong movement in some direction is going to have a large magnitude, whereas a very soft movement in a direction is going to have a small magnitude value. And the direction doesn't matter. And actually, when you look at this, I mean, so the magnitude is just computed as you take the square of your x your y and your z acceleration values, you square each of those and you sum them together, and then you take the square root of all of that entire sum. And so if you think about this, you'll never get a negative value with this, because you're squaring all of these values. And so if they're positive values, then positive squared is positive. If they're negative values, negative squared is going to be positive. When you're adding things together, you're never going to get a negative value if you only have positive components to that. So you always have positive values, and then you take the square root of something, and hopefully you never get a negative square root value. I don't think that's ever possible, or at least there's some kind of imaginary thing going on. But the end result is your magnitude is always going to be some positive value. You know, it has no direction. I can't tell whether this was a jerk up or down or left or right, but I don't care. I just know that this was some force that was applied, and it was either a big force or a little force, just based on how large that magnitude value is, how much larger than 0 it is. So let's just start with that. I'm going to take a Circuit Playground board, and let's just compute the magnitude of the XYZ accelerometer axis values, and we'll just graph them with Arduino. So we'll just look at that graph over time, and then we'll come back and we'll play with some of this filtering to see how that changes it. So I'm going to plug in this Circuit Playground board right here, and we'll go into the Arduino IDE. And you're going to need the Circuit Playground library installed. You're going to need to be set up to program Circuit Playground with Arduino IDE. And again, this works with both Circuit Playground Express and Classic. I'm using the Classic board here, but this will work with either of those. But as a pre-step, make sure that you've set up the Arduino IDE. Follow the guide, the Circuit Playground guide. That will show you how to set up Arduino to program Circuit Playground. And then in the examples for the Circuit Playground library, if you go to Hello Circuit Playground, let's just do this Hello Accelerometer example. So this is an example that just reads the XYZ axis of the accelerometer right here, and it just prints them out on the serial port. So actually I will just load this onto my board. So just make sure I have Circuit Playground selected as the board to program, and that there's the port. Yep, that's all selected. And so let's upload this, although I'm going to change the serial port baud rate from 9600 to 11500. That's just a faster baud rate, just so I can see the updates a little more quickly. Although this will only print it out every second. There's a delay in the loop, so every second it's going to print out the XYZ acceleration values. So if I open up the serial monitor, then we're going to see every second it's showing the acceleration values. And so this is kind of cool. I mean, you can see on the z-axis, I'm seeing an acceleration of like 9.6, 9.7, something like that. That's because the z-axis is the up-down axis, and so the force of gravity is pushing down on this board, and so that's why you see about 9.6 meters per second or so squared going down on this board. And then the other axes, if I change the orientation of this board, you can see it kind of changes. Now it goes down to like 9.4, something like that. So you get different values here as you rotate this board around. Okay, so that's how you read the accelerometer, but it's not just the raw XYZ values that I want. I want to compute that magnitude. So let's compute the magnitude of the acceleration vector. So all these fancy math terms, but at the end of the day, I just need to take the square root of the sum of the squares of each of these axes. So to do that, we'll say our magnitude value equals the square root function. And then I'm going to use the power function, to just do the square of each of these values. So we'll say x raised to the power of 2 plus the power of y, or y raised to the power of 2 plus z raised to the power of 2. And so then we take the square root of all of that, and that's going to give me my magnitude value. So now then, let's just add that to the printout here. So we'll say serial dot print, oops, it's going to print the z value. Let's print this after the z value. So we'll print that out, and then let's print a couple spaces, and then we'll just say mag, and then let's put serial dot print line the magnitude value. Okay, so that, let's load that onto the board, and then this is just going to show us that magnitude value that's been computed. So now if I open up the serial monitor again, so now you can see, here's the magnitude value, and you can see it's pretty close to the z-axis value, this large value, and that's because the magnitude, think of it as, look at the x and the y-axis here. These are kind of small values. They're close to 0. so they don't really change the value that much. You take the square of 1.4, so 1.4 times 1.4 is going to be, I don't know, like 2 or more like 3 or something like that. So a lowish value. And then you add that to 1.0 squared, so that's just 1. So maybe like a value, you've got a sum of like 3 or 4, but then take 9 squared, so 9 times 9, you get like 80 something. So that's a very large value. Add all that stuff together, take the square root, and so you can see the square root is kind of or the magnitude, which is the square root of the sum of all those squares. It's roughly equal to kind of the z-axis value when the board is held just steady like this, because the other axes aren't really applying much force to this. They aren't seeing really any movement or force. It's really just the z-axis that's seeing all of the force, and so the magnitude is roughly equal to that. But if I start moving this board around and shaking it and things like that, which maybe you can't really see, but if I shake this board, then you can see I'm getting all these kind of larger magnitude values. And let's actually make this a little more apparent. So I'm actually going to delete everything in here that I'm printing out. I'm only going to print out that magnitude value. And let's just remove this delay, or well, let's put in a 20 millisecond delay. So this is 50 times a second. This is going to print out the magnitude. So it's just going to constantly print out the magnitude of this. So we'll see a much faster printout. But instead of using the serial monitor, let's use the serial plotter in Arduino, and that's going to graph this value over time. And again, it's only the magnitude that I'm looking at. So let's open the serial plotter. It's not the serial monitor. Now I want the plotter for this. And so this is cool. This is showing the magnitude. And you can see as I move this thing around, the magnitude jumps up and down. Notice the magnitude is never negative. Like the board, I'm holding the board just kind of flat like this. And so you can see, I'm getting a magnitude value around 10-ish, which makes sense because the force of gravity is 9.8 meters per second squared, and it's going down like this. But if I flip the board upside down, the magnitude doesn't really change. It's still around 10 or 9.8 or something like that. Whereas, if I was just looking at the raw z-axis acceleration, it would be negative now because the board is flipped around and gravity is still going down, but the accelerometer is flipped around relative to gravity, and so now it would see a negative value. But again, because I'm computing the magnitude, I'm kind of resilient to that. Like I don't care about the orientation of this thing, or even if I hold this board at kind of a slight angle, or even just like straight up and down. So I can hold it flat like this, and I get a magnitude around 9.8-ish. If I hold it straight up and down like this, I still get a magnitude around 9.8 or so. And that's because gravity is still pointing down. My accelerometer axes have kind of changed their orientation, but the magnitude doesn't care. It's just looking at what is the size of that force that's applied to this thing. So that's kind of cool because, for example, if just to really maybe show the difference of this, let's just also print out the z-axis. So we'll say print the z-axis value, and then we'll put a comma in here so that we can see both these values. And the nice thing is with the serial plotter, if you put a comma separated list of values, it will plot both of those as different graphs or different series within the same graph. So if I open the plotter now, so now you see two things. The blue thing is the z-axis acceleration value, and the red thing is the magnitude. So if I flip this upside down, notice my z-axis just turned negative, like we're down in the negative values, but my magnitude is still up in the positives here. And if I turn this thing back to the other direction, then we jump back up to a positive value. So again, you can kind of see this is nice by just computing this magnitude. It doesn't really matter the orientation of this board. I'm just looking at what's the raw force that's being applied to it as I move this thing around. So that's a good way if you're just looking at like force and you don't care about orientation, consider using the magnitude like that. Okay, so that's the first step that they applied in the algorithm for this. And then the next thing that they applied was a low-pass filter. Because if we go back and we look at the serial plotted data, let's go back and open that serial plotter again. Let's look at serial plotter, there we go. So, imagine the board is on a shoe, and I'm going to jerk the shoe up and then down, and it goes up and down and up and down and up and down. And you can see this signal is kind of noisy. There's a lot going on here. At least it changes a lot. Like you can see there's a big spike, and then it jumps back down to a small value, and so you get these really kind of high frequency oscillations. And so that's what this low pass filter that the algorithm applies will try to get rid of. So we try to ignore a lot of these high frequency oscillations. So, imagine as I'm moving the board up and down and kind of, in a step-like motion. So this is me kind of moving the board as if I was taking a step. And you can see, I get all these little peaks and things like that. But let's see what happens if we apply a low pass filter to this to see if we can smooth this out so that we don't have as high of these jagged signals. We get something that's a little bit smoother that we can apply just a threshold to say, okay, once that smoothed value goes above some fixed number, then let's consider this a step, for example. Okay, so in the paper, they actually have all the code, which is, again, this is why I really liked this paper. If you go into the sensor data folder, they actually have the filter algorithm that they implemented here. And this was all in high-level Python code that they were using. They were using Matplotlib and SciPy, which is the scientific computing stack, to implement this. But in this lowpass.py, it shows how they implement this filter, and it's just using what's called a Butterworth filter. And again, I mentioned I'm not a signal processing expert, so I'm sure I'm going to get a lot of the terminology wrong on this. But this is a type of filter that you can use to create one of these low-pass filters. And the nice thing is it's actually built into the SciPy package and Matplotlib and all these tools, so that you don't actually have to code that whole algorithm yourself. You can call a function, and this is actually the function right here that says, hey, give me a Butterworth low-pass filter at this cutoff frequency, and it gives you back all these number values. What they're actually, these coefficients we'll look more at. And then given those coefficients, you can implement a filter. There's a standard algorithm for it, and you can filter your data. So let's look at actually something that I did. So I created, this is an IPython notebook or Jupyter notebook, and I've talked a little bit about Jupyter. It's this nifty little scientific computing notebook where you can run Python code and do things like graph data. And so what I did was I took the filtering algorithm in the setup right here. This is the exact same code that's from the paper right here from this lowpass.py. And I put it into this notebook so that I can kind of play with it myself and just look at, what happens when I apply this filter to some data? Like, how does the data actually change? So the first step is actually defining what are the parameters of this filter. Like I said, this is a low pass filter, so it's going to allow low frequency changes to pass through the filter, and it's going to reject high frequency changes. So something that moves really quickly, that's a high frequency. That thing should be rejected so that my filtered signal is not influenced by that high frequency. But if something moves a little bit slowly, that's a low frequency signal. I want that to pass through. I want to get that low frequency, that step data. Because when you think of your foot moving, you're probably moving like once a second, maybe twice a second or so if you're really moving. So that's a slow movement versus, you could be seeing very high frequency, thousands of times a second, different changes and things. So the actual the parameters for this filter kind of control what frequencies does it let pass through this filter. There are a few different values that define for this filter how it works. So there's an order, which for digital filters kind of defines the complexity of the filter, is maybe the best way I can describe it. The higher your order, the more advanced your filter can be, because there are kind of limitations when you're defining these filters. There's no perfect filter where you can say, given an input of data, I want to exactly pull out this single little range of frequencies, and I don't want to change the signal at all. I want the signal to be exactly the same, but I only want to see this little bucket of frequencies. I'm sure there are ways to do that, but they're much more advanced and require a lot of math and processing to do that. So there's a trade-off here where the order of your filter, the higher the order, the more complex the algorithm is, the more previous inputs it actually needs. Because the way that these filter algorithms work is they remember the old input values, and they actually sum those together with these filtering coefficients, and it actually remembers not just the old inputs but also the old outputs of the filter, and it actually sums together the old inputs and the old outputs and applies some scaling and some coefficients to it to generate a new filtered value. And so, that order defines how many of those old values does it need. Does it need 3 old values if it's like an order 3 filter? Does it need 200 values if it's like an order 200 filter? And just the more values, the higher your order, the more advanced your filter can be. So like with a low order filter like this, there's a limit to what kind of frequencies it can reject and how fast it can respond to frequencies and things like that. And there's also the phase of the signal changes, which is kind of like where the signal's oriented in time. You don't really have to get into all of this deep knowledge of this because this is really signal processing 101 type stuff that you can get pretty advanced with. The tough thing is I wish I could link to like a good signal processing for mere mortals kind of explanation of this stuff, but I really cannot find any good explanation that would take you from no knowledge to at least basic knowledge of signal processing. Everything jumps immediately into the math of it as far as like, oh, well, it's just differential equations and duh, everyone knows how to do that. We'll just apply all these equations. And of course, if you take the integral of this, you'll figure it out and make it work. And it'd be nicer if someone had an explanation that was a little bit less in the math and more of like, what does this thing actually mean? But hopefully I can show a little bit of that in this notebook here. But anyways, so the filter parameters, order is important. I'm picking an order of 3 because that's what they used in the paper. So if you go through this adaptive filtering paper and you look at the filter they used, they had an order 3 filter. The type of filter matters. If you go through the code for this in this low pass filter, like I said, they're using this Butterworth filter, which is just a type of digital filter. I don't even necessarily think it's a digital filter. It's a type of low pass filter that you can create in digital signal processing like this. And then there's this FS value, the frequency, the sample rate of your sampling. So how often you're reading the accelerometer, basically, because when you create this filter to generate these coefficients that actually power the filter, it needs to know, well, what's the rate that the data is coming into the filter at, because it changes those coefficients and it changes the behavior of this filter. So I need to tell this filter generation, okay, I'm sampling this accelerometer, let's say 50 times a second or 100 times a second or 10 times a second. I need to tell it that data. And that sample rate is also important because the way signal processing theory works, if I'm trying to detect a signal, there's a limit to what frequency signal I can detect based on the speed at which I'm sampling. And it's basically, you can only detect or reconstruct a signal that's half of your sample rate. So if I'm sampling 50 times a second, I can only at most deal with signals that happen or change 25 times a second. And that's fine in this case because, like I said, with the step detection, I'm probably never going to step more than 25 times a second. If I'm moving that fast, then I'm probably in a car or something like that. So, I know as a human, I'm only going to change, maybe once or twice a second. So 25 times a second, that's a pretty good upper bound on that limit. But in order to sample or in order to deal with a signal that changes 25 times a second, I need to sample at twice that rate. So I need to sample at 50 times a second. So that's an important value to know. And that also needs to kind of change my Arduino sketch so that now I need to be careful and make sure that I sample at exactly that 50 hertz rate or 50 times a second so that my filter is working the way I expect, because this filter is going to be built with the assumption that the data is sampled 50 times a second. And then there's a cutoff frequency that you define. And basically, this is where do I want that low pass filter to apply the filter. So do I want all the frequencies, in this case, the value is 3.667. Do I want all of the low frequencies that are 3.667 hertz and below? I want to pass all those through. And then anything above 3.667 hertz, anything that's moving faster than 3 or almost 4 times a second, I want to reject. I want to remove those from my signal. So that's what this cutoff frequency does, is it basically says, okay, this is the frequency where, the frequencies that are less than this get passed through, and the frequencies that are higher than this don't get passed through. Now, in practice, this filter is not that binary. It's not an on-off. It's not everything 3.6667 and below gets passed through, but if you're 3.7, you immediately don't pass through. There's actually kind of a shape to this filter. And you can actually see down below in this graph, it actually graphs out the response of this filter. And so you can see, this is showing on the bottom here, signals of different frequency. And then on the left here is kind of the magnitude of that signal. And so just imagine if I tested this filter by sending in different frequency signals and then measuring what was the output that I got of that signal, if I start with low frequency signals, so a signal that's changing, once or twice a second down here on the left, then my output values, I'm sending in an input with a magnitude of 1, I'm getting an output with a magnitude of about 1. So it's passing through that low frequency unaltered. But then notice as I increase the frequency, so right here is that 3.667 cutoff point. When I get close to that point, now my signal's reduced. So, I'm sending in a signal that has a magnitude of 1 at the left here, but it's changing at a frequency of like, let's say 4 hertz. And you can see the output is actually, it's not 0, it's not off, it's not, completely down to nothing. It's reduced, it's like half, it's, around 0.7, or it's, it's a smaller value at this point. And you can see there's a curve to this, so that as the frequency increases, it slowly drops off and decreases until eventually once I'm up in the 15 hertz range, I'm effectively down to like a 0 value in my outputs here. So I've filtered out all those high frequency values. But you can see how this filter has kind of this shape to it, and it's not perfect. So it's, it's as I get close to that cutoff frequency, it starts to reduce the signal, but it's not gone entirely. And in a lot of cases, you might want that behavior. Like you might want this kind of soft fall off. And like I said, like there's not really like a perfect filter that is just a complete brick wall of you either have it or you don't have it, because those kind of things don't really exist in the analog kind of filtering world. It's very rarely that kind of black and white on-off signal. It's usually something in between or something smoother here. And this digital filter is trying to emulate some of these analog filters in this case. But anyways, that's what these parameters mean. So by tweaking these parameters, I can change the behavior of this filter. And so the parameters are set just based on what this paper picked ahead of time, just based on what they saw. So with a sample rate of 50 hertz, a cutoff frequency of 3.667 hertz, and then there's an assumption, it's not shown in the parameters here, but this is a low-pass Butterworth filter that they're applying to this. Now they implement this using SciPy, which is this really nice library in Python that lets you do all the scientific computing, and it has this very full-featured signal processing library built into it, which can generate and apply all these filters automatically. And so that's what they've done in this paper. I'll put links to the important functions they use are this L filter function, which applies a filter to a signal, and this butter function, which generates a Butterworth filter, a low pass filter. You can actually, they're different. You can do a high pass filter, you can do a band pass filter, all different types of filters. But this is a way to generate a filter. And so these are the two functions that the paper used. And again, you don't need to understand all the details of this. I'm really just trying to get at like, what is a low pass filter here? Okay, so then in this little notebook, I just generated some random sample data here. I took a couple sine waves and I just added them together. But I took 2 sine waves of different frequencies. So I took on the left here, this is a sine wave that changes twice a second. And if you look at the math for this, I'm taking the sine function of 2 times pi times 2 times time. And so this 2 is basically my frequency of my signal. So this signal is going to change twice a second. It's a sine wave that's going to go up and down twice a second over time. And then I add to that a cosine value with a much higher frequency. So this one changes 20 times a second. That's the frequency value here. So this signal has 2 components to it. There's a low frequency sine wave that changes twice a second, and then added to that is a high frequency cosine signal that changes 20 times a second. So the actual signals, you'll see both. You'll see this low pass, or you'll see that low frequency, that low sine wave, but then on that sine wave, you'll see these little oscillations up and down, and they go, with the sine wave, but you see kind of this fluttery, up and down, noisy kind of signal, but it's changing at a much higher frequency. And that's actually this bottom plot down here. So I'm using some of these matplotlib tools to plot. At the top here, this is the response of that filter that was generated. And then down here, this is really interesting. So in red, this is my unfiltered sample data. So that's what I generated up here. And that's the low frequency plus the high frequency sine and cosine wave. And you can see that in the signal. Like, just ignore the green line, look just at the red line, and notice how, the red line moves at this kind of low sine wave twice a second frequency. So, and if you count how many peaks occur within time is on the bottom here, within 1 second, I see 2 peaks of that red signal. and that's because it has that low frequency twice a second component to it right here. But then also notice how jaggy it is. You know, it's changing twice a second, but as it changes twice a second, it's also changing a lot more than twice a second. You know, you have all these spikes up and down, and that's the high frequency noise. That's that 20 times a second cosine component that's added to this wave. And so that's what you see there. Now, the really cool thing is the green line here is the filtered value. And so that's basically taking, given these filter components, these parameters to my filter. So I want a 3.66 hertz cutoff frequency with a Butterworth low pass filter. When I apply that filter to that red input signal, the green output is what I get. And this is really cool because notice how the green line is basically a sine wave that changes twice a second. It's effectively this component of my input signal, but only that component. It's cut out the high frequency component. You don't see this cosine component that changes 20 times a second. You only see in this green line the actual twice a second component for this. And let's play around. I can change this data. So like let's increase it so that both of my signals change really frequently. Let's go from a oh, let's see, can I change this value? Oh, I can't do that right now because I need to have matplotlib running. Oh darn, I killed my matplotlib notebook. All right, well we'll run this. We'll get this going because I want to actually show this. I'm just gonna real quick take a quick diversion so that I load this up. And sorry, not my matplotlib notebook, my Jupyter notebook. This Jupyter notebook is actually available on GitHub. I'll put a link in the description below. All of the code we're going to look at is on GitHub, and so if you want to play with this notebook yourself, you can do that. But real quick, I'm going to run Jupyter notebook in this directory, and this will hopefully open up. Yeah, there we go. Okay, so if I open up my notebook, now I can actually run the Python code inside of here because I'm running their tool. Okay, so let's change our signal here. So let's change this so that I have two high frequency signals. Let's change my my sine wave 10 times a second and my cosine wave, the cosine component of it, 20 times a second still. So I'll generate my data. Oh, and it's mad because I need to go through and I need to rerun everything in here. That's just the way Jupyter works. When you open a notebook, you need to go and rerun everything that's been run before so that it gets your kernel back in a good state. Anyways, let's run this thing again, and now let's plot our data. So let's go through and run this graph. And okay, so now you can see here's that output again. And so again, the red is my input signal, and the green is my filtered value. And notice my filtered values are mostly around 0. Like there's a little bit of kind of some twiddle up and down to it, but not much of a change there. That's because my signal is really only a high frequency signal. It's only changing, or it's changing, you know, 10 times a second plus that 20 times a second component to it. So it's just a really fast signal. And this low pass filter sees that it's changing really fast and it just rejects it all. I mean, almost all of it, because again, you saw that, you know, it's not a binary on off, you know, you're in or you're out. There's that gray area, this in-between area where you're sort of in, you're sort of out. And you can kind of see that as these little small little dips in the green line where, you know, it's around that 10 hertz frequency, like right around here in my signal response. There's some component that gets through my filter, and so that's why you see the small change there. Now let's set this down to like all low frequency data. So let's go back to that twice a second value, and let's just remove the cosine component that was added to it. I'm just going to comment that out. So now I'm only sending in a signal that changes twice a second. So we'll do that and we'll replot it, and then we'll see that, yeah, okay, you know, here's my input signal in red, which changes twice a second, and my output signal in green changes twice a second. And so there's really no change in that signal. Now you might notice the signal's kind of shifted a little bit so that, you know, my input signal is the red signal, my output, my filtered signal is the green one, and the green one matches the red, but it's shifted in time. It actually happens a little bit after my red signal. And that's just a side effect of the way these filters work. So a lot of these filters, like this Butterworth filter and the way you implement them, can have an impact on the phase of your signal, which is how your signal is in relation to time. And so with this filter, it actually shifts the phase of your signal where it kind of slows down the signal in the sense where I can get a filtered value, but the filtered value is actually for something that happened slightly in the past. And this is just kind of a trade-off of filter design where, again, like I said, there's no perfect filter where there's no phase change and it's, you know, it's exactly the frequency response you want, or at least if there is a filter like that, it's very advanced. For these simple filters like this Butterworth filter and the way that you implement them using this infinite impulse response, you can get things like these phase effects you see here where the filter is applied to the signal, but the phase of that signal changes so that the signal is slowed down a bit. And there's a trade-off here. You can characterize filters and you can figure out exactly what is that phase shift. And you can understand like, okay, is that like, you know, a tenth of a second where maybe it doesn't matter because it's just my foot moving, and if it lights up a tenth of a second after it detected the movement, then that seems okay to me. Or is it like 10 seconds where it's like, okay, that's quite a bit in the future. That phase is way too large. And it turns out the phase shift here, I mean, you can see just looking at this, I mean, it's well under a tenth of a second. So it's pretty small for this filter, and it doesn't seem to matter much for us. But it's just an interesting property of filters. And if you get into digital signal processing, you know, the phase is a very critical component of it. Okay, so let's go back, and just to show, you know, we'll go back to the signal that I had with the high frequency component and the low frequency component. And so again, you can look at that graph and you can see the low pass filter works by cutting out all that high frequency noise and just passing through the low frequency noise. Okay, so now the question is, they did all this stuff in Python in this paper. How do I do that on Arduino and Circuit Playground? And so that's a little bit trickier. So now I need to figure out, how do I implement this filter in Arduino? Because I don't unfortunately have SciPy and Matplotlib and all these advanced Python libraries on my board. Even in CircuitPython, unfortunately, as far as I know, no one has plotted or has ported SciPy over to CircuitPython or MicroPython yet. And even if someone could, it would be pretty advanced, and probably you wouldn't have the memory to use something that advanced. So now the problem is, how do I take this filter and run it on my Arduino? And luckily, with a lot of this digital signal processing and filtering, there are basically two standard types of digital filters. And again, I'm not an expert on these. I'll probably butcher some of the description of this a lot, but from what I understand, there's a type of filter called an IIR, an infinite impulse response filter. And there's also another type called an FIR, a finite impulse response filter. And I believe the difference between those filters is effectively what knowledge it needs to implement that filter. With an FIR filter, I believe it only needs its previous output filtered values to generate a new filtered value. So it needs to remember, what was the output of my filter the last, you know, maybe 10 times in the past, and it uses those to compute the next value. So it has to remember what were my 10 previous filtered values, and it stores those. And whereas the IIR filter needs to know also its previous filtered values and its previous input values. So it actually needs to store more previous knowledge. And so given the previous inputs and the previous outputs, it can sum those together with all these coefficient values to generate a filtered value. And there are trade-offs to each. From what I understand, FIR filters have different phase responses versus IIR filters. There's differences in the complexity of how you implement those filters. You know, with an FIR filter, you only need to remember some number of previous outputs, whereas with the IIR filter, you need to remember some number of previous outputs and previous inputs. So there's, you know, maybe an increase in memory of things you need to store in that case. But when you implement a filter, an IIR filter might require less values versus an FIR filter that's trying to do the same thing. So there's a lot of trade-offs, a lot of complexity that you can get into with filtering. And again, I wish there was a simpler explanation of it. But the end result is, the way that the SciPy tool works, or the SciPy package works, like that butter function that I mentioned, it will generate these what are called coefficients. These are these numeric values that you can feed into an IIR filter algorithm, and it will apply that filter to it. So you can use this SciPy butter function to say, okay, generate a Butterworth filter at this frequency, you know, given a sample rate of some rate, you know, give me a low pass filter, 3.667 hertz, and this will give you back this set of numbers, these coefficients. And given those coefficients, you can actually implement that filter yourself. And the nice thing is, in the filter function here in SciPy, or actually it's lfilter, I believe is what they call it, this actually tells you how SciPy implements the filter algorithm. And so it turns out it uses that IIR, that infinite impulse response filtering algorithm. So it expects to have coefficients for an IIR filter. Luckily, that's what that butter function generates. So you call the butter function, you get those coefficients, you feed those coefficients into this filter function, and it basically runs this algorithm or this equation on your input data. And it's kind of complex, and I looked really hard for a simpler explanation of this, but again, everything dives straight into the math for it. So, but effectively what this is doing is it's taking the sum of your previous input values, and for each of your old input values, and there's only some number of old inputs, and that's actually based on the order of your filter. So for an order 3 filter, I'm going to store 3 of my old inputs. And for each of those 3 previous inputs, they each have a unique coefficient that's multiplied by them. So my first previous value has 1 coefficient that's multiplied by it. The next oldest value has another coefficient that's multiplied by it. And then, the third oldest value has a separate coefficient that's multiplied by that. So you multiply all your old values times your coefficients, and those coefficients are what you get from that butter function, that Butterworth filter generation function. And then you sum them together. And then, since it's an IIR filter, an infinite impulse response filter, you also have to take the previous outputs of the filter and do the exact same logic, but with a different set of coefficients. So you have 2 sets of coefficients, these A and B coefficients, and you basically take your old inputs and you multiply that times your coefficients and you sum them together. And then you take your old outputs and you multiply that by another set of coefficients. And you sum those together, and then you actually subtract them from your signal, and that gives you a new filtered value. And so that gives you a new value, this yn value that you get out of here. So that's ultimately what you need to do, is to use the SciPy, the Butterworth function, to generate those coefficients, that A and B set of coefficients. So there are 2 sets of coefficients. And then given those values, I can feed those into an Arduino sketch that implements that IIR filter. And the nice thing is, that IIR filter algorithm is generic. Like, it just needs to know what are the coefficients that you fed into me, and I'm just going to apply that math to my input signal, and then it's going to give you a new output value. If I want to change the behavior of that filter, I just need to change those coefficients. So I just need to go back and use that Butterworth signal function to say, okay, maybe I want to change that frequency cutoff from 3.667 to maybe like 5. Let's increase it to a higher value or something like that. So I just regenerate my coefficients. I feed those new coefficients into my IIR filter function, and it's going to apply that logic to it. The code doesn't need to change. It's just those numbers. It's just those coefficients that change. And you can actually see those coefficients in this IPython notebook. So I generate them right here. And so I'm calling that Butterworth filter generation function. And you have to pass a few things into it. You need to pass the order of it. You specify your cutoff frequency as a kind of a percentage of how close to your Nyquist sampling rate. Again, I'm not going to get into all the details of this, but basically, this is like, this depends on how fast you're sampling the data and what frequency you want for your cutoff frequency. Again, it all just comes back to this order, FS, and cutoff value that I set ahead of time here. So if I change these values, I can regenerate these coefficients by just rerunning this code against those old values. But this will just print out, okay, here is your A set of coefficients. And so I get 4 coefficient values out of here. And then here's my B coefficients. So for a 3rd order filter with this IIR implementation, you get 4 coefficients, both an A set and a B set of values. And so these are just magic values. Like, you can stare at these values all you want, and you probably won't understand what they mean. Even a signal processing expert probably won't understand what they mean, because you're not meant to know what these coefficients really mean. You just need to know that they were generated to approximate a Butterworth low-pass frequency filter at a certain cutoff frequency. So it's really just the output of that filter generation that you see as these magic number values. But the nice thing is, all different types of filters can be boiled down to different magic numbers, these different coefficient values. And so that way, when I want to change my filter, I don't need to go and change all the code for that algorithm. I just have to change the coefficients. I just build new filtering coefficients, pass them into my algorithm, and everything will work. Okay, so now how do I implement this in Arduino? And so that's where I get into some of the fun of this project. So let's open up a sketch that I have. Let's see, let's open one of the recent ones. Let's do this Arduino filter test. So all of these are on GitHub. I'll put a link to the GitHub repository, but you can actually see it right here if I go back to Adafruit's GitHub account. It's under this Circuit Walker Sneakers repository. So I'm going to look at the Arduino filter test sketch inside of here. And basically what this sketch does, that's the example. What this sketch does is it applies that infinite impulse response, that IIR filter, to the accelerometer magnitude. So earlier we were looking at a graph of just the raw magnitude, and you saw as I move the board around, you get that real spiky kind of shaky values. But if you open this sketch up, you can notice how I have some configuration values now at the top where I say, okay, what is the sample rate that I want to achieve for my accelerometer? So I want to sample 50 times a second. And again, like I mentioned, this number is important because the filter that I generated depends on the sample rate. So if I change this sample rate, I have to go and change that filter and these coefficient values. So you probably don't want to change this sample rate, but it is there to tweak and adjust if you want. And then down below, I have my coefficient values, that filter A and filter B values, which I've just directly copied out of that little Python notebook that we were looking at here. So I copied out, here's my filter A coefficient values, and I copy them out and I paste them into here. And make sure to surround them in brackets like this. They have to be comma separated. You don't want A equals, you'll get a compile error like this. You want in brackets like this. But these were the coefficients for that filter that was generated. And then the rest of the sketch just implements this filter. So I'll walk through this, but first let me just run this sketch. So let's load it onto my board. And you're not seeing all of the code here. There's actually another file, this irfilter.h. So we'll look at that in a second. But let's upload this to my board. So I just make sure I have the board selected. So I'll do that. And then I'm going to open the serial plotter again. And we'll see two signals that are going to be plotted. So if I open up the serial plotter, so you're seeing a couple signals in here. So I'm going to hold the board like this. You're noticing a blue signal and a red signal. And so if I move the board around a lot like this, and actually if I slide the slide switch into the off position. So if you don't see anything when you open the serial plotter, move the slide switch into the plus or the on position, because that's when it will start updating the graph. If I slide the slide switch off, the graph actually stops updating. It's kind of nice that I can stop the graph and we can look at the data. But I'm going to shake this thing around a lot, and then I'm going to stop it real fast. So let's look at this data. In blue, you can actually see the raw magnitude of my accelerometer values. And so that's exactly what I looked at the start of this video, where I compute the magnitude. You take the square of each XYZ axis values, and then you take the square root of the sum of all those values. And oh, here comes the cat. She's ready to inspect the sneakers here to see what she wants to do. But that's what the blue value is. That's my raw magnitude of my accelerometer value. And you can see how, it's kind of shaky. It changes a lot. There's some of that high frequency components to it. Now in red, that's the second series of data. That's the filtered output. So I'm taking that accelerometer magnitude and I'm putting it into that IIR filter algorithm that's been told to use the coefficients that I generated for that 3.66 hertz low pass filter. And now you're seeing the output of the filtering. And this is actually kind of cool. You can actually kind of tell here, remember when we looked at it in this little synthetic example in the Python notebook, I see the low frequency change. I don't see the high frequency, the big red spikes, but then I also see it shifted in time a little bit so that, my filtered value happens a little bit after my actual value changed. And I can see that if I go back to the serial plotter, wherever they hid that thing. Let's see, let me close that sketch. It's behind one of my windows here somewhere. There it is. So you can see that in the serial output here, in the plotter output. So the blue signal is my magnitude, and the red signal is the filtered value. So notice the magnitude right here kind of spiked up at a slow rate, And then in the filtered value, it also started to spike up at a slow rate, but it happened a little bit after the fact. So notice, this kind of started to jump up at this point in time, whereas in the filtered signal, it started to jump up a little bit later in time. And that's that phase shift that we see from the implementation of this filter. So my filter sees things that happened, a little bit in the past, basically. But it's kind of cool that you notice, like in my blue signal, it falls down to this kind of sharp spiked value, whereas in my filtered output, it goes down to a less intense, a less sharp value right here. And so that's kind of cool because it's showing me that, this filtered value is only showing the low frequency kind of change. I don't see the high frequency noise, the quick little shakes and judder and movement from my hand. I'm just seeing maybe a slower movement here. And I'll turn this thing back on and we'll just kind of see. It updates kind of quickly. So but you can see, if nothing's really changing, or even if I'm moving this thing kind of slowly up and down, not much really changes, and the blue line pretty much follows the red line. But if I start shaking this thing a lot, then you can see how the red line sort of follows the blue line, but it's softer. It doesn't move as much. And that's the low pass filtering. So, we're filtering out that high frequency shaking that's happening, and we're just looking for what's the lower frequency change in movement. So maybe my hand kind of moving up and down at a slower rate like this. And so you can imagine if this was my shoe and this was, on my shoe and it jerks up kind of quickly like this. So I'm just going to move kind of up and down like this, and I'll see if I can turn it off so we can kind of look at that data. So we'll kind of move it up and down. Oh, I think I just accidentally killed the serial connection. Let's reopen this. Let's open the serial monitor. Oops, I meant to open the serial plotter, that is. Let's open the serial plotter. There we go. So I'll see if I can turn this thing off. So I'll kind of move it up and down as if I was taking some steps. We'll see if we can kind of change this thing. Okay, there. So I just moved it. So you can kind of see here, we're getting, here's the blue is the original signal, the magnitude of the accelerometer, and the red is the filtered value. And so you can kind of see, yeah, there's some little sharp peaks here, but then the filtered value removes those sharp peaks, and you just get that more slowly changing signal. Okay, so that's pretty cool. Like, this has implemented the filter. Now let's see, I'm starting to run a little bit late on time, so I'm not going to go into all of the details of the implementation of this, but I wrote it in such a way where you could take this filter code and change how the filter works just by changing these coefficients. So like I said, this IIRfilter.h, this is where I implemented that infinite impulse response filter. And I really just went through and literally just implemented what they mention in the SciPy docs right here. I just implemented this equation right here. And I walked through it in this IPython notebook where I actually did a Python implementation of the IIR filter because, I'm going to implement this thing on Arduino, but it's a lot easier for me to debug the Python code. So I implemented that filter in Python, and then I just plotted what's the output of that filter. And so this is actually kind of cool because this is actually showing what's the output of, from my input data. So that's that red signal right here. What's the output of it given my IIR filter implementation that I wrote myself versus the one that Matplotlib or SciPy has internally. And it looks like I expect. I'm seeing that twice a second kind of frequency where, I've filtered out that high frequency noise. Now you can see there's still a little bit of that high frequency noise in here. Again, the filtering is not perfect. And there's some trade-offs here with like the accuracy of the numeric computations and things. But it's still pretty close. I mean, I'm seeing that slower change here. And so that's exactly what's happening in the implementation of this filter in Arduino. So you can see this is kind of the Python code version of that filtering code. And then if I go back to Arduino and if I close that, then this is the Arduino version of that code. And so this filter function is what applies that filtering logic. And like I said, really the way that this IIR filter works is it just needs to remember the previous inputs and the previous outputs of the filter. And then it needs to know what were the coefficients that are assigned to each of the inputs and output values. And it just multiplies and sums all those things together. And so that's what it's doing. So when you create an instance of this IIR filter class, you have to pass in the A and the B filter coefficients. And so that's what's happening in the sketch. It's kind of hidden from you right here, but right here is where I create this filter. And I'm doing all this templating. I'm doing some advanced stuff here. Where basically, you know, I'm templating the filter order with some C++ fanciness here, which you don't need to worry about, which is a nice thing. But if you want to change and adapt this to different size filters, you might need to change the order of your filter. But that's what these numbers are. This is a fourth, or this is basically telling me how many coefficients I expect for both the A and the B coefficients of this filter. But anyways, you know, I'm just in my constructor, I'm just storing those coefficients. You know, in this class, I just remember your A and your B coefficients. It's just an array of those numeric values. And it's exactly these values right here that get stored for this filter. And then in the computation here, I'm keeping track of the X array has my previous inputs, the unfiltered values, and then the Y array has my previous outputs, the filtered values. And so really the way this filter works is it just sums together my inputs and my outputs, and it multiplies them by the different coefficients that are associated with each to get a final output value inside of here. So that's the way that this filter works. And the cool thing is, you know, again, like notice, like this code, nothing in this filter code knows that this is a low pass filter or that it has a 3.66 hertz cutoff frequency. You know, this algorithm is generic. It's just implementing that infinite impulse response filtering. It's just these coefficient values, these magic numbers that change how this filter works. And so that's really the big thing I wanted to get across in this video, is that, you know, you can do some of this advanced digital signal processing and you don't necessarily need to know how this filter is implemented and like what the actual code of an infinite impulse response filter looks like, or a finite impulse response filter. You just need to know, you know, me as a user of this filter, I really just care about like, what is the cutoff frequency? What are the characteristics of this filter? You know, is it a low pass filter? Is it a high pass filter? What signal is it going to let through? And, you know, how can I change that value? How can I generate a filter? And then once I generate a filter, I just need to know I get these coefficient values. I feed them into this class, you know, this IR filter class, and it will go and apply that filter. You know, it's going to look at those coefficients, and I will get behavior that matches the filter that I modeled and I generated ahead of time for this. And then just real quickly, I'll just jump through the loop code for this. It's very similar to what we wrote just a moment ago. You know, I'm computing the magnitude of my accelerometer values, just like we saw before. In this case, I'm doing it in a slightly different way. I'm calling on the Circuit Playground class. We have this LIS 3DH accelerometer object. So you can call the read function on that to say, hey, read your XYZ accelerometer values, because this reads all three at once, so that I'm not getting weird out of phase values. So I read my XYZ acceleration at once, and then I compute the magnitude of that. And then in my filter, I just call that filter function that we were just looking at, and I pass it in. Here's my current magnitude, and it returns back, here's your filtered magnitude. And it will keep track of what were my old inputs, my old outputs, all those coefficients. It does all that math, and it gives me a new filtered value back that I store right here. And then I just look to see if my slide switch is turned on or off. Then that determines whether I print out my values or not, so that I can view them in the serial plotter like this. And then all of this logic is just happening in this loop, and I have a little check at the top where I only want to sample my accelerometer some number of times per second. So it's defined by this sample rate up here. Because remember, I built this filter with the assumption that my incoming data changes 50 times a second. So if I change this sample rate, I actually have to change my filter coefficients to match that. And it's not the kind of thing where I can just intuitively know, oh, if I double my sample rate, well, then I have to go double my coefficients. I've actually got to go rerun all those math functions again and get a whole new set of coefficients. You're going to get new magic numbers basically for this. So, you know, you're not really in practice going to be changing your sample rate. But it's also a constraint where I need to make sure that my sketch runs and is sampling 50 times a second, no matter what else it's doing, like whether it's animating lights and, you know, other things that are happening. I still need to make sure that I'm sampling data and passing it through that filter function 50 times a second. But that's what this check does right here, is I just figure out at the start of my loop how much time elapsed since the previous loop iteration, and if I've seen enough time elapse since my last sample, you know, then I go and actually generate a new sample and do all the filtering and logic for it here. So that's what this filter test example does. Again, you know, I'm just looking at, in the serial plotter, the filtered output of my accelerometer. so that I can see when I apply that filter to this, and if I get some really high frequency data and then lower frequency data, that 3 hertz or 3.6 hertz low pass filter seems to be doing what I expect here. Okay, now at the very end of this, I'll show the last sketch is if I open up the, let's see, this is the step test example, and this is in the GitHub repository right here. So here's the step test example. So this is just like the filter test example we looked at, but I just added a threshold value into here. So I define a threshold of 1.3, and this is another magic number, but this is basically if my filtered magnitude of my acceleration goes above this threshold, I consider that a step and I turn on the neopixels. And so that's actually the code that's running right here, so that when I sharply move the foot up and down, you can see it turns on red, and that's from this sketch. And so it's doing the exact same thing. It has the exact same filter coefficient. It has that IIR filter.h built into it. So it's applying the same filtering logic. And now my main loop is just a little more complicated, so that, you know, I'm still running at that 50 times a second. I still have my sample rate hertz, but now 50 times a second, I grab my magnitude of my accelerometer, I apply my filter to it. I still print out the values, so I can still open up the serial plotter here if I want and see the output. Well, I guess I don't have my shoe connected to this right now. I can still see that output. But then I look and I see if my filtered value goes above my threshold, then I need to turn on the neopixels, like turn them red. And the way that this works is I turn on the neopixels for a certain number of milliseconds. It's defined by this step flash milliseconds value. So 750 milliseconds, a third of a second, basically. So if I see a sharp jerk in acceleration up, then it will turn on the lights for a third of a second, or sorry, for 3/4 of a second rather. So 750 milliseconds. And so it's just doing that by saying, okay, I'm just going to say I keep track of how long the pixels have been turned on red, and at the start of my loop, you know, if my pixels have been turned on, I set a time limit. I say, okay, turn on the pixels red for 750 milliseconds, and if I have a countdown effectively, and so every time my loop runs, it will just subtract how many milliseconds elapsed from the amount of time that the lights have been turned on. And then once it gets below 0, so once my lights have been turned on for 750 milliseconds, it turns them off, and it just stops counting, stops keeping track of how long the lights have been turned on. So that's really all that's happening here. And then so when I pass that filtering threshold, I basically set that timer to say, okay, turn the pixels on for 750 milliseconds. It's going to start counting down with the future loop iterations. And then it turns on the pixels by just looping through all of them and setting them all red. So this is the red color that it sets right here for that. So that's all this sketch does. You know, this is the start of the circuit walker sneakers, because you can see, you know, as I'm moving my foot, it changes kind of the behavior here of this. You know, I get that jerk up, and I get that kind of it detects it and it turns on the lights. But also notice, you know, as I jerk it down like that, you know, if I step down, like if I touch the ground like that, that's detecting as that jerk and movement. And so that's just an interesting way that this works. You know, it detects the motion up and the motion down. So depending on how I tune this, you know, I could have it so that, you know, you lift up and it does an animation really quickly, and then you hit the ground and it does another animation potentially. There's lots of interesting things we might do in the future with this. But again, this is the basic example. I just wanted to show how do I take this adaptive step filtering algorithm that we looked at here and convert this into something that I can run on Arduino. So we looked at, you know, how does this algorithm work? And again, we're only looking at the first half of this algorithm where I'm just doing this simple threshold. I don't have any of this adaptive logic. I'm not sure yet if I need this adaptive logic. I'm going to play with it more on my own time, and maybe in a future video we'll see if adding that adaptive logic makes sense. Because right now, how sensitive this thing is, you know, does it detect a slow jerk up like this, or does it detect a really fast jerk? You know, how strong of a signal does this have to be is determined by this threshold value. And I mentioned in the comments here, if you increase the threshold, then you're going to need a stronger kick up to set off the step. Whereas if you decrease this value, then a much more subtle, you know, if you're just a very quick or a more soft step would set this off. So increasing and decreasing this value is something worth playing with. And you might have to tune it to kind of how your steps go. You know, if you have very hard steps, you might need to increase this threshold. Whereas if you have very soft steps, you might need to decrease this threshold value. So, in the future, I'm going to look and see if does that adaptive logic actually help, like does it make it so that it can detect hard steps and soft steps, or is it just unnecessary? I'm not sure myself if I need it or not, so we'll see in the future if I do. But this is a good example of how can I apply digital signal processing, that basic low pass filtering, to the accelerometer on Circuit Playground. And we saw the output of, once I apply that filtering to my signal, how does it change it? What, as I move this thing around, what does that output signal look like? And then what can I do with that? And when we dove into how do you build that signal, and so you can look at this IPython notebook that I linked to, and on the GitHub repository, you can actually just click the Circuit Walker Sneakers filtering.ipynb, this file right here, and GitHub will render it. You can't change the code when GitHub renders it like this, but you can at least see how I generated these coefficients yourself. But we saw, it's just using some of these functions that are built into some of these scientific computing packages that know about all of these digital signal processing concepts like infinite impulse response filters and Butterworth filters. And I can use all those things to generate my filter coefficients, and I can even model them. I can figure out, given some sample input, what does the output of this filter look like? I can, make sure that this is really the filter I want. I can look at the response of it. When I'm happy with that filter, I get these magic numbers. And then we looked at in this Arduino sketch where I've implemented that IIR filter, I can pass in these magic numbers and apply that filter to my code so that now when I move this board around, it applies that filter and I can do different things with it. So that's all I wanted to do. If folks have questions, throw them in the chat. Looks like it's been pretty quiet, so I don't see too many questions. So we'll jump back to the main shot real fast. And I think I'll wrap up this stream. Yeah, I don't see any questions in the chat. So thanks a lot for watching. This is Tony from Adafruit. This was part 1 of the Circuit Walker Sneakers project. So I want to take a new spin on an old project, the Firewalker sneakers, basically sneakers that light up as you take steps. And so you can see as I move this sneaker around, the board lights up and flashes. And this is using Circuit Playground. This is Adafruit's all-in-one electronics learning board, which has an accelerometer that can detect forces and movement and motion, and NeoPixel, so it has little lights that can light up on the board. And all of that's built into the board. I don't have to solder anything together. I've literally just zip tied to the shoelaces this board, and there's a little battery that's just hidden that I have inside the shoe, and that's it. I didn't have to glue things onto the shoe. I didn't have to fine tune some Velostat and all kinds of fancy stuff. But this is kind of cool. This is going to be the start of what should be a neat project, because like I said, this is part 1. We looked at the algorithm. Part 2, I'm going to look at maybe some fun animations I can do with this. Maybe have it like sparkle and glow as you move your foot and as it detects steps. And then, like I said, in part 3, I'm going to see if I can do an implementation of this in CircuitPython. That's going to be tricky because this IIR filter, as we saw, there's a lot of math involved with it. And math operations are not super fast in Python because it's all interpreted code. So we're going to see, are there maybe different ways or different approaches that I might take where maybe I don't have to use that IIR filter. Maybe there are other things I can use that don't need my code to run as fast, but can still detect a jerk and movement potentially. So we'll look more in the future at that. Anyways, though, so check out youtube.com/Adafruit. You can see this video, all kinds of other fun project videos. Check out twitch.tv/Adafruit. You'll see me stream these things live. I like to stream usually every Friday. I'll do a live stream. And like I said, this will be part 1 of a multi-part series on the Circuit Walker sneakers. If you find this interesting, then click the like, the comment, the subscribe button. Let us know that this is good content, and we'll keep making stuff like this. Until next time, this is Tony from Adafruit, so thanks a lot for watching. I'll see you later. Bye.